the title is just a different version of the broker I'm going to introduce. So many of you are aware that with LSST and actually CTF already, there is going to be an avalanche of data coming, and in particular, every night we will have the order of 10 million events coming that we will have to ingest in a system and attempt to classify and help astronomers do the follow-up. So there are several teams today preparing for this. We are one of them, and we are applying to become one of the LSST brokers, but we're currently ingesting the CTF stream. So our broker is called the ALeRCE, Automatic Learning for the Rapid Classification of Events. ALeRCE is a tree in Chile. And as you can see, it's a very large collaboration of people in astronomy, computer science, electrical engineering, mathematics. So it's a really exciting project, and also with many institutions in Chile and also in the US, and some people here as well. So the outline of my talk is, first, I will, just to introduce you to the ALeRCE project, I will briefly talk about HITS, which is where we come from. There was this previous project looking for supernova in real time. And then I will explain more about ALeRCE, and then if I have time, I really want to do a demo, and so see if we can show you some how this is working. Yeah. Okay, this is the ALeRCE tree, as I was mentioned to you. It's like the equivalent of redwood here in the US. Okay, so first the high cadence transient survey. This is a survey that we ran in 2013, 14, and 15 using the dark energy camera for 1 week each year, more or less, and 1 hour cadence approximately. So this is the motivation was to study the luminosity versus timescale diagram, and we're interested in particular in the early hours of supernova explosions, so the shock breakout that is called. So this area was basically unexplored at that time. Now we know that there's kilonova, we know more about shock breakouts, and there are other events, but this is what we did then. And the strategy was the following: was point the telescope, certain region of the sky, do 5 epochs per night. So, and as you get the data, ingest it, and run in real time pipeline, image difference pipeline, and machine learning real bogus classification with some nice visualization tools, so that you could react and take the phone and call the 8-meter telescope and say, okay, take a spectrum. This was done in 2014 and 15 in real time, and 2015 we really have made this work with a nice visualization tool. So this showed us that visualization was very, very important. Okay. Okay, so this is how the data moved from the slew. You take exposure of 87 seconds, read out, transfer data to La Serena from CTIO, then to Santiago. Now you're in the cluster, run the Deccan community pipeline, remove cosmic rays, do the image difference pipeline, and then you have 2 minutes to do visual inspection before the next image comes. So you have this happening one after the other. So when you're looking at images, the telescope is about 4 fields ahead. And this is the number of pixels we collected with candidates. Then you use machine learning, raised to 1 million. And if you require the candidate to be present twice in the same location, this goes down to 10,000, and this is manageable. It's about 2 or 3 candidates per every 2 minutes. And in the end, we discovered 125 supernova. So in this part is where the machine learning comes in, the real bogus classification. We first use a random forest classifier, and then we switch to deep learning. So I will show some of the work we have done on this. Oops. Okay, first. In 2016 and 17, Guillermo Cabrera Vives, together mainly with Ignacio Reyes, they developed this deep HITS as a rotation invariant convolutional neural network for transient detection. I mentioned this because it has already mentioned, but I would like to show this previous work as well. And the nice thing about this network was that it was built to be invariant to rotation. So each image was rotated 3 times and went in parallel in this network, and then finally gave one answer, real or bogus. Then Esteban Reyes improved this and introduced this cyclic slicing and pooling, and made this even more robust, and also added interpretability using this layer-wise relevance propagation. So you can actually see for every stamp what are the pixels that are actually making the network decide that this is true or false? And Esteban got to really quite impressive numbers, 99.53 accuracy of F1 score. Then also Pablo Joyce with Pablo Esteves in Chile, they use like unsupervised classification using variational autoencoders, and basically with 2 parameters in the latent space, you can actually do quite a good separation. And then semi-supervised, Nicolás Astorga, using this deep variational embedding, where in the latent space you have a mixture of Gaussians. He also achieved a very good score and require very few labels to actually classify. Okay, so there are 5 different publications on this from the group in Chile. But okay, so in terms of science, we achieved many interesting results. So the driver was astronomy, really. But in the process, we ended up with some nice results in terms of machine learning. So here you can see show breakout constraints, many distant ALeRCE found by Gustavo Medina, who's in the audience, new asteroids, public catalog of variable stars. We found that the shock breakout models were wrong. That we require something new, a circumstellar material surrounding type 2 supernova. And also, I will show later, an image sequence classifier. So combining a recurrent and convolutional neural network for classification of time series. And finally, also a new population of intermediate mass black holes that is accepted. Okay, so now we'll talk about ALeRCE. So as I mentioned, we started with this project HITS, High Cadence Transient Survey. We are producing about 100,000 alerts per night that we need to classify. With CTF, we go up a factor of 10. Actually, in the public stream, this is not a factor of 10, but in total, I heard it's a factor of 10. And with LSST, there is another factor of 10. So we need to really ramp up quite quickly here. But all the experience that we gain here, I think we can use it for doing this better. So what is the future of time domain ecosystem? So basically, there's a new layer that we are going to start building. You have basically survey telescopes, the ones that are studying and producing detections of new objects, variable objects, not only in optical, but also radio and gravitational waves. And then there is a layer of follow-up telescopes that want to follow the most interesting objects. But of course, if you have 10 million per night, it's very difficult to do this. And for this, we require this new layer of brokers and TOMs. What are TOMs? TOMs are target and observation managers. And basically, the TOMs are the systems that can actually talk to the telescope and that understand each individual telescope better. And TOMs are listening to the brokers. So brokers listen to survey telescopes. TOMs listen to brokers. In telescopes, listen to TOMs. This is the future of time domain astronomy. So why we're building a broker was, as you know, there's amazing infrastructure in Chile that we need to use and do efficiently. In Chile, we have access to 10% of the observing time, so it's really a big responsibility, and we need this broker. The team is quite large, as I mentioned, and here I show pictures of 3 different hackathons that we have already done, and these are the members and letters of support that we got, and the composition. As you can see, it's mostly statistics and machine learning, also astronomers, computer scientists, and in terms of roles, researcher, engineers, students. So actually, there are more students than is shown here. As I mentioned many times, the Agile methodology is really key. We started the project with the same mindset as we did HITS, but the scale of the project and the fact that you have to make this into production has other requirements that we had not encountered. So this is very, very important to have clear objectives, to have periods of 2 weeks where you work towards an objective. And also we play with different ways of visualizing Kanbans, and now we are using Project Wall, but we're continuously improving. What are the scientific questions? We want to understand transients, to do rapid photometric follow-up, to really get into the early time and see the outermost layers of the star, so we can tell what is the progenitor of the supernova or whatever exploded. We want to also look at variable stars. There are also some science cases where you need rapid spectroscopic or photometric follow-up. Microlensing, for example. There could be stars that change pulsation mode. You want to see that in real time. Or stars that stop pulsating or start pulsating because they must cross the instability strip. And also you want to have the ability to do a large analysis of large number of events to understand the structure of the Milky Way. This doesn't have the urgency of this previous part, but still, since you're classifying everything, you can also do this part. And also active galactic nuclei. There are also many reasons why you would like to do this rapid follow-up. There's changing look agents or changing state agents. You want to do reverberation mapping studies. And you will also find new populations that you have not seen before because you have so many of these events in the future. Okay, so we have a taxonomy that starts with an alert. We will try to say, okay, is it real or bogus? If it's real, is it transient or variable? So this is a different version of the ALeRCE taxonomy, but it's more focused on the transient side. In terms of transients, we can have gamma reverse, tidal disruption event, kilonova, or supernova. And supernova are also divided in many classes. So in the ALeRCE diagram, this is just one leaf. So for the people that is going to be the users of ALeRCE, I think we need a slightly different taxonomy. And of course, we cannot have all the taxonomy of this other diagram. It's just too complicated. And there's not enough data for the moment. Then there's also these objects between transient and variable, the eclipsing stars, pulsating stars of different sizes. And there's also the stochastic systems, things with accretion disk, where the AGN, young stellar object, cataclysmic variable live. So there are very different phenomena here, and you need to do this in real time and provide classification that the users can trust. So this is very challenging. How do you use ALeRCE? There are different ways. As I said, we ingest the stream of LSST or CTF. I didn't mention that we use in Apache Kafka, which is becoming the standard for this now. Then we have a front end where you can do a quick visualization. We provide Jupyter notebooks for different science cases that you can run locally, and also provide Jupyter Hub access, so in the cloud, next to the data. And finally, also the output stream that the rapid users need, the toms and the telescopes. So the infrastructure is mostly running in AWS at the moment, but it's composed of 5 big components. Basically, everything is run on services, microservices. We have Dockerized services orchestrated by Kubernetes. You have distributed messaging, which is Kafka, and distributed database that we are exploring Cassandra and Ignite at the moment, and also distributed storage. Last week, there was a meeting in Seattle about the brokers, and it's possible that some of these tasks will be shared among different groups. For example, the cross-matching could be done by 1 or 2 brokers. And storage, perhaps it's not necessary that everyone stores everything. And if you share resources, then you can allow more groups to come into this game. So what is the status of the classification of ALeRCE? At CTF, we're basically using 2 classifiers. One that is based on light curve, that takes into account all the light curve, and one that is based on images, that is only for the early times. So the idea is that the image has more context than the light curve. So if you use this information, you can do much faster classification. And then in the future, we also want to include, of course, outlier detection and forecasting service, like what Matthew mentioned. In terms of taxonomy, we have a very simplified version of the taxonomy. And the idea is that this will keep growing continuously, and as users require new classes. And the cross-match, we're just using the labels, but in the future, we want to use features to be input to the classifier. Okay, so this is the work by Rodrigo Carrasco, the recurrent convolutional neural network that I mentioned before. And the idea is this. Imagine you have the light curve of an event, and you want to classify it. If you only see the light curve, you don't really know if this is a variable star of some kind or supernova. And if you see the image of the difference only, you're left with the same information. It's basically the information contained in the light curve. But if I show you this, which is the science and template, you can clearly see that this is a supernova because of the context, right? So this information contained in both the images and the light curve. So for this, Rodrigo made this convolutional and recurrent neural network, that you have a convolutional part that looks at the information in the image, and a recurrent, the STM, that looks at the information in time, to do classification among different classes of transients and variables. And this seems to work quite well for the few examples that we looked. And as I said, you get this information sequentially, and the probabilities are going to be improved with time. Okay, so then we encounter the following problem. When you use simulated data, the recurrent convolutional neural network and the random forest seem to perform very similarly, actually. So the hypothesis that the images contain more information than the random forest seem to be not true in the simulated images. However, when you move to real data, which is this, so this is the number of images that you have in the sample, and this is accuracy, and this is recall versus number of sample. With real data, the performance of the classification model was not so good, and actually the random forest did better at some point than the recurrent convolutional neural network. However, if you add only a few samples per class, you can do fine-tuning of the network, and then the recurrent convolutional neural network works better than the random forest, especially at early times. So here. So this is what we were hypothesizing, and it turned out to be correct, that if you use the information at early times from the images, you can classify this better and faster. Okay, so in terms of training sets, I think this is a very important discussion for the future. We will have to build a library of training sets that everyone can use to train classification models. And it seems that you cannot have everything. So either you have models that are easy to obtain and representative of reality, or that can be good extrapolating and that contain physical parameters. Or you can have models that are very similar to the domain that you want to classify, or that have complex taxonomy. It's very difficult to have a complex taxonomy and live in the same domain as you want to classify. So here you have the direct cross matches. This is what we're using now, but you have few examples. You can also do data augmentation in this quadrant. In this quadrant, you can do domain adaptation, transfer learning. So it's very important. And in this quadrant, you can use physical models. And perhaps what Pablo's mentioned, embedding the physical laws in the system lives somewhere around. I'm not clear where it lives. But I think it's useful to have this taxonomy in mind. So now this is current version of ALeRCE. This is plastic. This is what we did in HITS. And this is the next talk by Manuel. Okay, now I try to do the demo. Let's see how this goes. The resolution. Okay, so first, I'm showing you 5 minutes. This is the front end. This is a previous version of the front end where you can see all the alerts of CTF and the density plot. You can see this in real time. We temporarily disable this to make this faster, and this is the current version of the front end. So okay, I'll load this. For example, I can say this is not the best resolution, but give me, for example, all the ALeRCE in the data set, and then I get some ALeRCEs. I can click. I can see. I don't see really anything periodic, but if I do folded, then I see the ALeRCE light curve. I can also say, okay, give me all the supernova that were discovered since January this year, the 1st of January. And here I get. And here is one. You see the supernova, and you see the galaxy here. Okay, so this is running now. We're now working on. Actually, we implemented this morning. the team in Chile. We're working with two types of classifiers. One that is an early classifier, that is shown here, In this case, it tells you, oh, it's probably a variable star. Very simple taxonomy. But also a random forest with the full light curve that tells you, okay, this is an ALeRCE. Okay? So it's consistent. And in here, if I do folded, you see the ALeRCE light curve. Here I have another example. This is the difference magnitude light curve that you don't see much. If you correct to build a parent magnitude, you see something, and you fold it, you see better. This is an LPV. The early classifier tells you, yes, the variable star. The random forest tells you LPV. And here I have some examples that with one image, the early classification tells you, oh, this is possible supernova. And it kind of makes sense if you look at the image. Another example. And it took me like a few minutes to get many nice examples thanks to this early classification. And I didn't have to even look at the light curve. Okay, so yeah. And here I have a notebook. Let's see if this works. And I'll show more examples of things, for example, that are supernova based on just one image. This is an example. Not always works. You see there's a problem there. This is a galaxy there in the background. This is another galaxy. You see a supernova. Another supernova. And sometimes you get bogus. But also we include in this the bogus class. And if we do again this. Oops. So you see examples of bogus that actually produced in the stream of LSST. This is with the previous version of the real bogus classifier. Okay. What else? We have some notebooks that are for different science cases. I don't have time, but this is an AGN use case notebook. You can see all the tables in the database you can access remotely. There is a supernova use case notebook, variable star use notebook, where you can see actually the periodogram, and you can ask iPaladin to show you the image. And we also have Jupyter Hub. This is the supernova use case notebook that is running in Amazon at the moment. So I can execute, and it takes time. Yeah. And I think I don't have more time. Do I have? Yeah. Yes. This is this one I wanted to show. Yeah.